Okay, so here's the thing. Also, fair warning, when I drop this book on this table, it will be loud. So if you are wearing headphones, I might suggest taking headphones out. Fair warning. Okay, here we go. Actually, I forgot. Before I drop them, in the chat, let me know what you think is going to happen. What's going to fall first? Is the book going to fall faster than the paper? Is the paper going to fall faster than the book? Or will they fall at the same time? Those are the three possibilities. At least realistic possibilities. I guess we could always drop them and all of a sudden a spaceship comes and catches it in its tractor beam and then they fall up, which I just don't think that's going to happen. A lot of people saying the book. Larry thinks that the paper is just going to fall to the side. It's not going to fall straight. Okay, but most people in agreement that the book will fall faster. Okay, let's try it out. And here we go. 1, 2, 3. Amazing. Fascinating. Try it again. 1, 2, 3. So if you are able to see that, if your lag on your video is not killing this whole thing, then you're going to see that the paper falls slower than the book every single time. Okay, so with this sheet of paper and this book is going to fall faster every time. Why? Because our data shows that heavier objects like a bowling ball will fall at about the same speed as a tennis ball. So why does this piece of paper take longer to fall? Any ideas? Post them to the chat, please. So Dylan's saying maybe we could crush it into a small ball. David's saying that the air. What about the air? Air is pushing against the paper, absolutely. One thing that we forget about sometimes, we are constantly surrounded by air, and air does have a little bit of mass. So that air is pushing up against the paper, causing it to fall more slowly. But like Dylan pointed out, maybe we could try making this piece of paper smaller. And keep in mind, it's the same exact piece of paper. It's the same exact mass. The only thing different now is the shape of the object. So we're getting rid of that large surface area that beforehand air was able to push up against. So now David thinks that the paper will fall faster. Now, remember, be specific. Are you saying that the paper is going to fall faster than the book, or that they will fall at the same rate? Okay, we got three options. Drop them both at the same time. Either the paper falls faster and hits first, the book falls faster and hits first, or they fall and hit at the same time. So let me know what you guys think in the chat, please. All right, so David said the paper first, but now he's changed his mind. And we got a lot of people saying that they will fall at the same rate, which would make sense because we have data that shows that that same thing happened with the tennis ball and the bowling ball. All right, let's try it out. Here we go. 1, 2, 3. I know it's kind of hard for you guys to see, but like I said, I encourage you guys to try this on your own if you don't believe me, but these two objects will fall at the same rate every single time. 1, 2, 3. There they go. And I do encourage you guys to give this a shot. It's kind of one of those weird things that it's just not really what you're expecting. So when the ball is crumpled up, it does fall equally as fast as the textbook. Absolutely, Larry. Perfectly explained. So we said that the reason that they fall at the same rate now is that the surface area of the paper is smaller, which gives less area for the air to push up against, which means that it is able to fall more freely. Excellent. And people agreeing with you, thank you for that.